Okay, now good morning. Start from the class where we left yesterday. We were discussing about applications of a stack, and today we'll do one more before we end this topic, and we'll move on to the other topic, which is nothing but queue. Now, just one application which remains to be done, which is a very important application of a stack. And it's also one of the algorithm which is most well-read algorithm called as the quicksort algorithm. Now today we'll discuss this algorithm here. That means quicksort algorithm is again an application of stacks. Now, why I am teaching you in this topic? Because it uses stack. Otherwise, this could have been covered in the last one where we will discuss some of the algorithms of sorting. But this is an important one, and therefore we'll try to make you understand that why it is an important algorithm. Now, I already told you in the very initial classes, the worst case sorting complexity of quicksort is order of n square. Therefore, when we say the worst case is order of n square, which is not a good algorithm because you already know that the worst algorithms are order of n square algorithms. But even if it is an order of n square in the worst case, we do not consider it as an order of n square algorithm, but consider it to be an average case of order of n log n. Therefore, what we are going to do is that we consider it as an order of n log n algorithm. Now, this is the average case for this. Therefore, we say it's an average case. The average case of sorting is order of n log n. And again, you know that the best algorithm ever designed are n log n algorithm. Therefore, if you take one, if you neglect one of the inputs, will come into the order of n log n. And all the empirical evaluations have shown that it is near to n log n in almost all cases except one. Now, let me try to show you that why it's an n log n algorithm and how you are going to use this algorithm for evaluation. Now, let us take into over here. I will try to let me just remove this. So you require the full board. Now, let us take down the problem which is I have an algorithm. These are numbers. Now, these numbers are the one which I am taking directly from the book. So therefore, you are going to use this book. So these are the 12 numbers which you have taken as an initial input. Now, what I will do is that I will try to sort it using quicksort method. Now, let us try to get the basic details of quicksort. What a quicksort will do, it will pick one of the element which might be the first element as a pivot element. The pivot element is the element which is taken as the first element in most cases, and we are going to find the appropriate position of that pivot element. Once I get a pivot element, I get the appropriate position. The list will now become divided into two, where all the elements less than pivot will lie on the first on the left hand side, and all the elements bigger than that will lie on the right hand side. That means the original list of 12 elements, you are going to get two sublists, which could be anything. It could be say 2, 9 or 4, say 4, 7. That means it will 12 minus, that means there are 12 elements, it will be having a two sublist of say combined elements of 11. Now, taking into consideration, what I will do is that I will take, suppose I take this one as a pivot. I take this one as pivot. And beginning with this pivot element, my aim is to find the appropriate position of 44. Now what I will do is that I will scan this list from this side, finding the smaller element from the pivot. That means I will compare 44 with 66. It is bigger. Then I move. I will start comparing with this. 44 with 66 bigger. Come to 88. Then I find it is also bigger. Then I will move to this 22. And I find this element which is smaller than 44 from moving from right to left. The moment I find the element which is smaller than that, what I will do is that I will swap them. That means what I will do? I will swap them. That means here I will copy 44 and here it will be 22. And rest of the element will be like this, same. Okay. Now this is the pivot which I have already taken here. Now this is the pivot. Now I will try to find an element from the opposite direction. That means what I will do, I will try to find an element from here which is bigger than the pivot. Now obviously you have to find the element bigger than the pivot. Now you cannot, don't compare with 22, already sad. Now you start from 33. This smaller, then I move again 11. Again it's smaller, I come to 55. And I now find that 55 is bigger than 44. Now I find that this is bigger than 44. Now what I am going to do, I will swap 44 with here. Then what I will do 44 over here and 55 over here. And rest of the element will be like the same. And this is the pivot. Again do the same thing. From right to left, find an element which is smaller than 44. Now you have to start from here because 55 is already swapped. Now 99 is bigger than 44. Move forward. 60 is bigger than 44. Again move forward. And you reach to 40, and you find that 40 is smaller than 44. And you swap 40 with 44. Now here what will happen? You will find, you will get 40 over here. You will get 40 over here. The rest of the element will be like this. And this is the pivot element. Now we again start from the right hand side and try to find an element which is bigger than this. Now you have already done if you compare with this. And you find that this is bigger than 44, you swap this with 44. Now what you are going to do is that you are going to swap this with 44. And now this is the pivot. Now again, start from here and try to find a number smaller than 44. Now you have only 190 is there. Therefore 90 is bigger. Then you move forward and you find that you have come to the same point. And that means once that the pointers, both the pointers meet, it means that there is no more elements. And there is no more elements. That means once this pointer is going to move forward and meeting to the same place, you find that it is no more there. And now here you find an interesting thing. What we find that all the numbers in this sublist and all the numbers in this sublist are arranged with respect to 44. That means all the numbers on the left hand side are smaller than 44. And all the numbers over here are bigger than 44. That means you get sublist 1 and you get sublist 2. And 44 is at the correct position. 44 has now come to the correct position. Now my problem has now become two sublists is there. One containing 22, 33, 11, 40. And second containing 90, 77, 60, 99, 55, 88 and 66. And now this is the pass one of the algorithm. Now what you will do is that you apply the same method on both the sublist individually. Now let me try to show you how it is going to work over there. Now what I am going to do is this, I will take these numbers 22, 23, 11 and 40. This is the sublist 1. Now what I will do is that I will take this as the pivot and from this side I want to find a number smaller than pivot. Now obviously I'll compare with 40, it's bigger. I'll compare with 11 and I'll find it smaller. Then what I do is that I swap them. 11 will come here, 22 will come here, 33 will remain as it is, 40 will remain as it is. And then this is the pivot. What I'm going to do, from this side I want to find a number bigger than 22. Now I will start from here and at the first point only I find that 33 is bigger than 22. Now what I do is that I am going to swap these two. And this is the pivot. Now again I start after 33 to find a number smaller than 22. Now after 33 is 22 only and therefore this is the same number. That means what I got here, this is smaller than 22. And this is bigger than 22. Now see, this is only one number. Now this is already sorted. This is already sorted. But this is sorted by chance. It will not be there. Therefore, in that case, if you apply the algorithm again over here, you find that if I take this 30 as pivot and compare with this, I will be able to cannot find. Now in that case, if I take this as a pivot and find a number smaller than 33 from the right to left, I cannot find. Therefore, 11, 22, 33 and 44 is sorted now. Now what I get is there, what I get over here is that I get this number as a sorted number. Now this is already sorted. This is sorted. Now, if you go from the back, if you go back, you find that this is already sorted. In the second pass. Similarly, you apply the same in this one, in the second sublist. What you will do? Take 90 as a pivot, try to find a number is more than 90 from the right to left. That means in the next year this will become the pivot. Then try to find number below less than 90, it is 66. Stack 66 with 90. Again 90 will come there. Start from this side, find a number bigger than 90. On the left to right, you will find 99. Swap 99 with 90, and you will again make two sublists. And at the end of doing this, making a sublist, you will end up in finding sorted numbers. Now what happens is that in the initial you had one list, you made into two. From 2, you made it into 4. 4 will make it to 8. And in each sublist, you find that there are at least one number. Now here, when I got 4 plus 7. 4 is there, 1, 2, 3, 4, 5, 6, 7. Divides into 4 into 7. Now when I am going to make the second thing, I find that there is 1 and 2. On the left hand side, you had one number. Here is now one number was 11. That means in this one you find a one number, and here you find there were two numbers. That means the sorting, the second sublist was sorted, second pass was sorted in 1 and 2, with 22 as the pivot. And by this method, you will end up in getting that. And after that, if all sublists are sorted, you just these numbers are already sorted, and you get it in a sorted way like this. Now this is simple sorting. This is algorithm, sorting algorithm. Works on the principle of divide and conquer. It works on the principle of divide and conquer paradigm. It's called a programming paradigm. Divide and conquer programming paradigm. Now till here, now the question comes, how I say that's an order of n square algorithm. Now let us take a worst case scenario, that where it will come as 3. Now let us try to find the complexity. Is the algorithm clear to all of you? That how I am trying to find the pivot and trying to compare. Now, how to find the complexity? Let us take the numbers. Say 4, say 7, say 12, say 20, say 28, and say 40. Here are the input values. Now, what I am going to do, I apply quick sort. So, what happens is that I take the numbers, I take this as pivot, and start comparing from this side. I compare with 40, it's bigger. I compare with 28, it's bigger. I compare with 20, again it's bigger. I compare with 12, again it's bigger. I compare with 7, it's again bigger. And I reach to this point. When I reach to this point, I find that all the numbers on the right hand side is bigger, where there is 0 number on the left hand side. That means my sublist will become like this. One sublist will be like this one, and one sublist will be like this. Which contains 0 numbers, 0 elements, and this contains 5 elements. And this is the pivot element, and you have 4 as a pivot element. Now what you do is that you again take the same numbers over here. You will find that I have the numbers over here 7, 12, 20, 28, and 40. You again take this is the pivot. Again try to find from the right hand side smaller than this. You will start comparing over here. 40 is bigger, 28 is bigger, 20 is bigger, 12 is bigger, and you reach to this point. And now again you find on the left hand side you have 0 numbers, on the right hand side you have 4 numbers. That means on before 7 you have 0 elements, then you have 7, and here you have 4 elements. And this will keep on going like this. You will find 12. Over there, you find that it's 12. from 12 you are going to get it. That means you get the pivot, and then again you are going to use the same concept. Which is going to make all as zeros, and the left hand side every time it will become a zero. That means the sublist is the sublist what you will get will be 0 with n minus 1 sublist. That means if we are having sublist of n numbers, we will divide like this. We will divide with 0 and n minus 1. And by this method, this is the worst case. Now let us come to the conclusion that why we say it's the worst case. So what happens? Let us try to understand the concept. If I had 6 numbers, how many times you compared in order to get the sublist? Now obviously, what you did is that you did 5 comparisons. You compared with this one, 1, 2, 3, 4, and 5 comparisons. Okay. Then in the second case, you did 4 comparisons, then 3 comparisons, then 4. Therefore, if I get a general formula for this, even has come. Now, when I get a general formula for this, what I'm going to get is that I am getting, say, n plus n minus 1 plus n minus 2 plus dot 1 comparisons, which is nothing but n into n plus 1 by 2, and this will be, say, n square by 2 plus n by 2. Now this is nothing but order of n square by 2 plus order of n. And you know that we have to take the higher powers, therefore it will be order of n square by 2 plus order of n. Now what, I remove all the constants. If I remove this one, I remove the lower powers, and this is the one I got as the complexity. This is what I get as the complexity. Now why this happened? Because you got in the passes you got n minus 1, n minus 2, and you keep on doing this many times, and in all the subsequent passes you end up in getting these numbers. But this will only happen if the list is sorted, because in that case, to find the correct position of pivot, you have to scan the whole list, and therefore this is the worst case complexity of the quicksort. And therefore, when you are going to apply this, then now the question comes: when will the complexity of the quicksort will be order of n square? It's only when the list is already sorted. It is already sorted. But if the list is not, if only one element is just modified, you will not get this one. Now it means that if the numbers are like this, suppose the numbers are, say, 2, 8, 15, and suppose if I get 12, 30, 40. Now they are the numbers. You find that all the elements are sorted except one. Now this is the one which is not sorted. Otherwise all the numbers sorted. In this case, even you will not get an order of n square. Now the order of complexity for this will be n log n. Even if one number is placed in such a way that the list is not sorted, this will end up in order of n log n. Now in that case, you mean that you are going to run the algorithm 100 million of times or maybe 100 times. If you give all input sorted, it is giving the worst case. Even if you are giving one number the unsorted, you will not get order of n. Therefore, we say that though in the worst case this performs an order of n square, but actually In the average case, it's an order of n log n. But the probability of giving all sorted numbers in a big list is very, very rare. And in that case, you will not get an order of n square. Therefore, strictly speaking, this algorithm is an order of n square. But practical point of view, this will be n log n. It will be n log n to the base 2. And I again repeat once more that the best algorithm it can ever be defined, which is based on comparisons, will never have a complexity better than n log n. That means you can never develop an algorithm better than n log n in any case if it is based on comparisons. That means this is the best time complexity. And always think that the best time complexity for any sorting algorithm will be order of n log n if it is based on comparisons. And the worst time complexity will be order of n square. The worst time complexity. Will be order of n square. Any algorithm between these two are good ones. Any algorithm better than worse than n square is totally useless. You can never have an algorithm better than n square. Now I asked you a question. In order to perform a searching algorithm, if you are trying to develop a searching algorithm, what can be the worst time complexity? What can be the worst time complexity? A searching algorithm. Yeah. Write your answers. What can be the worst time complexity for a searching algorithm? And what is the best time complexity for searching algorithm? The worst time will be order of n. And the best time will be order of? And what is the worst time? Sorry, best
Log n. Order of log n.
It is log n, correct. It will be log of n to the base 2. That means if you develop an algorithm of say bigger than log n times, it means that you are doing repeated work. Suppose if I develop an algorithm of order of 2n, suppose I develop an algorithm of order of 2n, such algorithm. What is the meaning? It means that you are doing n 2 times. I am searching once, not satisfied, again searching once, then I get that results. Then why this 2 has come? It should not have come. Therefore, it is the worst case. Suppose I want to search, suppose I take one roll number and try to find is the person in the class. What I will do, I will scan from starting to end and try to find it out where the person is there. Starting to end means there are n number of people in the class. Obviously, I will do it n times. Now, first of all, if I get 2n, it means I am searching once, not satisfied, again searching once, then I am satisfied. Then that means it becomes a 2n. Now, the worst case means in the order of n means you cannot have more than that. Similarly, you cannot have a better than log n, because log n is the best time complexity for any searching algorithm, and you know that binary search in the order of log n. Any algorithm between log n and n are very good algorithms. Any algorithm of searching between log n and n are very good algorithms. Any algorithm better than log n is impossible to design. Any algorithm then worse than n is totally useless. Now here, therefore, I say that algorithms are there, but this is a time complexity. Also, a space complexity is also there. In quick sort, there is no space complexity, because when you are going to sort, you are just using the same spaces. Therefore, you don't require extra space for this. And therefore, these algorithms, this quick sort is a very well-read algorithm and has been proved that this, for most of the cases, this will work perfectly. Now, this is the last one which I did. is the quick sort. And again, I say that it's a quick sort is the application of stacks. Therefore, we stop at this point and complete the chapter stack. Now, in the next class, when I come, I'll show you some questions which you will be able to do in that in that time. Now, the next topic which I start today is Q. And you know that again Q is a pure linear data structure. It's a pure linear data structure. Why I say pure? Because in that case you cannot even try to access the elements in between. Now what I'm going to do is that you know that the Q will have two ends. Now what I'm going to do, I will do like this. Now there are two ends. One we call it the front end, and one we call it a rear end. Okay, you can write the reverse also. You can write front that side or rear this side. But the meaning is that the arrow is the significant. Front means you are going to delete element from the front end. Rear means you are going to insert element from the rear end. All insertion will be done from this side, and all deletion will be done from this side. Now, whenever I am saying Q, it means it's a circular Q. Therefore, from now onwards, whenever I speak Q, it automatically means a circular Q. Circular Q means the ends are joined. That means it's something like this. Now suppose I am going to write like this: 1, 2, 3, 4, 5, 6, 7. Now I might write like 1, 2, 3, 4, 5, 6, and 7. I've just joined 1 and 7 by just folding it. Now Q is nothing. This is the Q. This is the Q. Now how will you interpret? Obviously, there will be two ends to this. One at the front and the. Now, if the Q is empty, now there are two pointers. One is F and this R. Now, if the Q is empty, both will point to say 0. If both points to 0, it means that Q has no elements. That means that it's an empty Q. An empty Q. Now, when you are going to translate into programs, you know that you have to write Q is F is equal to -1 and R is equal to -1. Because the index starts from 0. Now, once you are going to write algorithm, now what you are going to do is that we are going to write an algorithm for insertion. Now let us try to understand the way. Now what happens if I am having a circular Q like this? What I am going to do is that I am going to, first of all, the value of F and R will be 0. Now what I will do is that I will try to make it like this. Suppose this is the Q. So 1, 2, 3, 4, 5, 6. And then the max number of the space is 6. Now what you have to do is that you have to insert element. Initially F and R is 0. Now suppose you want to insert an character A. Now obviously A will come here in the first position, and F will point to this place, and R will also point to this place. That means you are inserting through rear, but also manipulating the front pointer. Front pointer will be manipulated only at the time of first insertion. After that, when you insert, you are not going to manipulate the front point. When the queue is empty and you are inserting for the first time, you manipulate both the pointers. Now, in that case, if f is equal to 0 or r is equal to 0, insert the element and set f is equal to 1, r is equal to 1. Now, suppose I want to insert b. I will insert b over here and real will come here. Now, real will come here. Now, suppose I want to insert c. C will come here. C will come here and real will now point here. Now again I insert D. D will come here, real will come here. Now again I want to insert E. Real will come here. Now suppose I want to delete one element. Obviously deletion will be done from the front end. I can delete, I will have to delete A only. I cannot delete any number, any elements in between. So what I am going to do is that I am going to delete A. When I am going to delete A, what happens? I am going to move the F over here from here to here. And now what I am going to do is that this is now deleted. Now again I want to delete one more element. Obviously what I will do, I will remove this element and I will remove this and F will come here. Now again I want to insert F. What I will do, I will insert F over here and real will come over here. Now real has come to the max. So here max, this is max. Now real has come to the max. Now if I had not deleted two elements, this would have been full. But there is no more element after max, but there is some element at the beginning of the stack. Sorry, beginning of the queue. That means how it is like this, you are having C over here, you are having D over here, you are having E over here, and you are having F over here. Now front is at this position and rear is at this position. Now I'll just remove this one so that you are not confused. Now you want to insert an element after R, but there is no space after R. Then what I am going to do is that I want to insert the element at this position. That means this involves that you are going to, suppose I want to insert a number, say suppose I want to insert a G. Now this requires that this R should now point over here. Now R we should move from there to there. That means what I was doing previously, I was incrementing the value of R to R plus 1. Because what I did, I was doing from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. But at this time, what I found that when I reach the maximum, now I have to reset the value of R is equal to 1. Because there is no space at this place. There is no space over here. But there is space at the front of the queue. Then what I do is that I have to reset the pointer. In this case, is called as a rotation case. Now, if you are doing a normal queue, rotation will not take place. Once this R comes to max, I say full. But in the case circular queue, this is an advantage that if there are spaces in the front, you can rotate the pointer and start writing from that side, inserting from that side. Now again I want to insert say H. I will get H over here. R will come to this place. I again want to insert say S. S will come here, and now this will come to R over here. Now this is the I will get R over here. And now what I get? These are all gone. And this is now the status of the cube. This is now the status of the cube. Now if I want to insert any more elements, I can't, because there is no space after S. And at this moment, you say that the cube is full. And at this moment, you can't insert until you delete some of the numbers, some of the elements. Now, in that case, this is the condition for cube full. There is one more case where it will happen. It will happen once you are going to insert and front points to 1 and rear points to max. For example, it's case like this. Insert say A, B, C, D and E. R is pointing to this place and F is pointing to this place. And this is 1, 2, 3, 4 and 5. Now you just try to understand why I am going to write like this. Now let us try to show you that why this is. I am going to use this concept very, very clearly to you, that this is one case and this is the second case. In both these cases, it is nothing but cube full. Now this is the first case, the case 1 for cube full, and this is the case 2 for cube full. Now what is the condition in the case 1? F is equal to 1 and R is equal to max. What is the condition for in case 2? Now you have to tell me. What is the condition for full in the case 2? If you say that, if whatever you will say, if it is correct, the algorithm is over. What is the condition to make sure that the case 2 is full? Anyone? What is the condition? Here I said if R is equal to 1, if F is equal to 1 and R is equal to max. Batao? Anyone can say? How will you detect whether the Q is full in the second case? Yeah. Now, obviously, both will be adjacent. But in that case, what happens is that the F will be at 4 and R will be on the right side of F. If rear is greater than front, okay. No, here is not greater than front. Okay, somebody wrote, yeah, F is equal to R plus 1. F is equal to R plus 1. That means front is bigger than R. It is only in the case when rotation has taken place. If F is equal to R plus 1 is true, it is the Q is full. Okay. Now, if you are going to make an algorithm for this, just combine these two conditions. And therefore, what I am going to do is that I am going to write the algorithm for circular Q insert. Therefore, I will just write the algorithm. Now check is the first one. What I will do is that I'll check whether Q is already filled. Now what is the condition? If front is equal to 1 and rear is equal to max. This is one condition. Or the second condition, or front is equal to rear plus 1. Then print circular Q is full. Q is full. And then you can return from there. Okay, you return. So this is the one we discussed in the previous one. That means either it's R, F is equal to 1 or R is the max, or it is the rotation case. Now, if it is not there, then what you do is that you have to find the new value of R. Therefore, what you do is that find the new value of R. Now, there are three cases over here. One is that if the Q is empty. Otherwise, it's a normal Q. And third, if it is a circular Q. That means the circular Q means rotation has taken place. Now, you have to check the conditions. If front is equal to rear is equal to, say, 0. Or I can say front is equal to null or rear is equal to null are the same thing. You need not check both of them, you can check one of them also, because if F is 0, R will also be 0. Therefore, I might write this whole, or I might write only like this, I might write like this, say I write F is equal to null. It means that Q initially empty. And what you will do if it is empty, what you are going to do is that you set F is equal to R is equal to 1. Okay, this is a normal Q. Well, I just write the comments over here so that you will be able to understand this thing. I will write this comments. This is Q is empty. Then the second case, I have to check for normal Q. The normal Q is the one where you find that you will say over here you will say else it is not true if rear is equal to rear is equal to max. What is the meaning? Rear is equal to max means it is equal. That means it's a case of rotation. Then put R is equal to 1. Now this is the case of rotation. Now the third one is normal case. Else just put R is equal to R plus. And this is the case for a normal. Now this was the second. The step was the now 2, I'm writing 3. Then what I now what I can do is that so write the 3, insert element in the queue. Now you know that insertion is done through the real pointer. Therefore, I say that if I take the name as say Q, the name of the area is Q, then I say R is equal to the element you want to insert. And that's all, you stop. You stop. Now this element has to be read by you from the keyboard, or you have to pass it as a parameters. If you want to pass it as a parameter. Now, if you want to use like this, now try to understand one more concept. What are the variables if you are implementing it as a function? Now, it means that those things has to be passed as a parameters. Now, what are the parameters you need to pass? You just check it out. Then what I am going to do is that I am going to write the list of parameters over here so that it will be easy for you to understand. I write the parameters. What are the parameters? Obviously, you have to pass the Q. Then you have to pass max. Then you have to pass front, rear, and element. Now the variables I'm using F, I'm using R, I'm using max. Okay. Then I am in the next one. I am using the parameters over here Q, which is array, and the element. Here are the only 5 variables. 4 of them are normal integers: front, rear, max, and element are integers. Q is an array, or Q might be a linked list. That is a 2 ways to implement. But what I am trying to say, if I am implementing as an array, Q is an array because I have written as an array over here. That means out of this 5 parameters, it has to be this one, then integer. This is also an integer. This is also an integer. This is also an integer. This can be an array. Or it could be a pointer also. But when I am writing over here as an integer, it means that I am trying to use that as an integer. Now this is the normal method of writing algorithm. Now if you are going to write a program, you write a main program, then you write this function circular Q with all these parameters, integer Q of say size, some size 10 or blank. You can also write like this. Now if you are going to do this, you can write like this. Let me just show you what in 1 minute how I write. Suppose I write say integer, say Q. You might write say integer, say the parameter is Q, integer max, integer F, integer R, integer element. Or maybe if I'm doing it like this, I will write say character, say element. Why I wrote character? Because I was inserting ABCD. Now in this one you are going to write, just convert the, the algorithm to a program. And this is so simple that you cannot even think of. What you have to do is that you just write this line. If x is equal to 1 and r is equal to max, then then printf q is full, return 0. Then you write if f is equal to null, okay, you have to put double equal sign, then f is equal to r is equal to 1. That's all. The third one, you just say else if I is equal to max, I is equal to 1, else I is equal to r plus 1, and after that put a semicolon, then q of r is equal to 11, and that's all. You just write 5-7 lines from there, and your function is ready. And you use you are using a switch case to call this function. If you understand the algorithm, converting to a program is a child's play. If you know just the syntax, you can directly convert. And this is how we are going to. Therefore, what I am trying to say is that why we are not writing a code in C, because if you know just a basic syntax, also you can convert it. Now you have to just write the semicolons over there. Equal to will be replaced by double equal to, and so on. That's all. Of course, then will not be, you don't write then, and you remove all this. Now this is a circular Q insert. Now stop at this point. Tomorrow we'll do the circular Q delete, and that will be. Now after that we'll do what we'll do is that we'll be writing some applications of queues. Now